Well, I'm very thankful to have had two wonderful talks covering the observational aspects of superluminous supernova as a nice introduction, and I'm thankful to have a chance to tell you a little about some of the modeling work and trying to understand what powers these events. I'm going to talk mostly about these engine-powered events, magnetar-powered events, and I'll leave discussion of interaction to Stan. And as we heard, the magnetar-powered model can fit, fairly well some of the gross properties of these supernova light curves, their peak brightness, the shape of their light curve. But we'd like to do a little better than that. I mean, the data, as you've seen, is getting quite detailed and specific, and we'd like models that made more detailed and specific predictions about signatures that you may see, that you may actually be constrained about that. So I'll tell you a little bit about recent efforts to try to come up with some more intricate predictions of these models and how they may interface with the data. But you'll see that there's still a lot of questions to be raised. Before I get to the complicated model, let me do the simple as zero-order model. If you want to model a supernova light curve in one equation, here's your equation. That's almost all you need. The luminosity you get out of a supernova is basically the energy you deposit in it over the time scale it takes for that energy to diffuse out, which will depend upon the mass and opacity and velocity of the ejecta. But there's this term in brackets here, which is like an efficiency term. So if you dump in the energy too early before the radiation can escape, the ejecta will expand, and all that internal energy will go to kinetic energy as you do PDV work. And for these homologous radiation energy dominated gases that we have, that efficiency is basically just the ratio of the deposition time to the diffusion time. So if you want to make a luminous supernova, you can't just have a lot of energy to play with, you have to have good timing too. You have to dump in that energy roughly when the ejecta is going translucent so that you can get a high efficiency of radiation. And that's the main point to make. So that's, leads to different ideas of powering events through different sorts of continuing energy deposition. So radioactivity, which I'll just say briefly to show that it can explain some of the supernova we see, and I'll talk mostly about the engines, some continuing energy input from, say, a neutron star or maybe a black hole. And then, as I said, I'll leave Stan to talk about interaction models and pulsational pair. I will mention that some of these supernova that they're seeing now, if you integrate the total radiated energy, it's something like several times 10 to the 51 ergs. In some events, maybe pushing 10 to the 52 ergs. And even if your timing's good, you're not going to radiate at 100% efficiency. Maybe your typical number might be like 30% efficiency. So the total energy budget in these supernovas is something in excess of 10 to the 52 ergs, which is quite a bit more than we think you can get out of a normal neutrino-driven core collapse supernova. So it's likely that an engine, a magnetar, or black hole is implicated in one way or another. That is the question, just to get that energy budget up. So the question is really whether what we're seeing from the luminosity is continuing activity of that engine, or whether that engine just shot out some material that later collided with other things. And both may happen in different scenarios. So we heard the different sorts of events that have been observed. Here's just a sample of different luminosities and durations. If you want to explain them with radioactivity, you need quite a bit of radioactivity, several solar masses of nickel. There is a very strong upper limit to the amount of nickel you can make in blowing up a star. The total mass you can make cannot exceed the total mass of the star. That stands to reason, and it's actually an interesting, meaningful constraint. If you plot that constraint on this curve, this line here is a total nickel ball. All the ejecta is nickel. And the point is that as you try to add more nickel to make it brighter, you also make this remnant more opaque, and the diffusion time's longer, so you get a longer duration thing. So these type 1 superluminous events that are quite luminous and also very quickly evolving simply can't be explained even with a perfect ball of radioactivity. There's just not enough energy per unit gram in radioactivity to power these events. So you need a more potent source of power, and that could be a central engine, say a rapidly spinning magnetized neutron star. This is not an exotic idea in a sense. We see it in our own backyard. This is the Crab Nebula, is exactly that, a supernova remnant being powered by the spin down of a neutron star. And it's actually tapping that spin down energy quite efficiently, I understand, something like 30% efficiency. So the question is that not whether this happens, this is happening leisurely over the course of 1,000 years for the crab. The question is whether you can soup up these magnetic field strengths and these spin rates to get a lot of energy out on a time scale of months like we see in the superluminous events. And so the basic ideas go back to work done in the 70s, Ostreicher, Gahn, and Bodenheimer and others, who thought maybe pulsars did everything. Maybe they gave the energy to blow up the supernova, maybe they powered the light curve. And the idea is you have a pretty high energy budget to play with, with. If you produce a neutron star spinning at millisecond rotation speeds, which is about the limit that the neutron star can spin before it starts shedding mass, about a millisecond, you have energy of maybe of order a couple times 10 to the 52 ergs to play with in the kinetic energy of that spin. This may reach even higher, 10 to the 53 ergs, as recent work suggests for sort of more massive neutron stars, depending on the equation of state. And that energy will be tapped if the thing is magnetized due to magnetic dipole spin down on some time scale that depends upon the magnetic field strength. And so for superluminous supernova, to get that sweet spot of having the spin down time scale match the diffusion time scale, we want magnetic fields of about 10 to the 14 Gauss, so sort of weak magnetars, and fairly rapid spins, maybe millisecond or so spins. Now that's a nice picture. There's a lot of questions you might ask about how that all works in detail, and there's a lot we don't know. You know, how does the energy dependence of that deposition work? For a vacuum dipole spin down, there's a simple equation that the luminosity goes something like 1 over t squared. These magnetars are not dipoles in vacuum. There's stuff around them, and it's not clear that this simple equation should be applied blindly. In fact, some pulsars we see spin down with different exponents, but some behavior of that form is expected. And then how does that energy from the magnetar spin down actually get transported and heat the ejecta to be radiated? This is where Robert said that the tooth fairy came in and did it for you. There is some physics here, although it is complicated and not totally well understood. Basically, the energy is coming out of the magnetar as a very magnetized wind, mostly pointing flux, and somehow that gets dissipated through instabilities or reconnection or something and produces high energy particles, electron-positron pairs. Those will cool quite rapidly due to inverse Compton synchrotron radiation. And basically at the end of the day, you get this big pool of hard radiation, gamma rays, X-rays, UV radiation, basically spanning the whole electromagnetic spectrum. That's sitting in the center of the ejecta. And just like the gamma rays from radioactivity get absorbed in the ejecta and heat it to power the luminosity, here the non-thermal gamma ray, X-rays, and so on from the pulsar wind nebula can get absorbed and power the emission in the optical. This was worked out in nice detail and described in Metzger 2014. And there will be some inefficiency here, just like the gamma rays can escape from nickel in late times of type 1a supernova, and maybe the gamma rays and X-rays and other things can also escape the ejecta of a superluminous supernova at some times, producing perhaps some X-ray signature to be seen, or also affecting the optical luminosity. And finally, you might ask where that energy gets injected. Just about every model assumes it's just a spherical deposition. You might expect, if you have dipole spin down, that it's something more bipolar-like, and that may have some influence on what we see. So I'll touch upon some of these questions as we go along. But before, let's just take the kind of first order model, where you have the spin down formula, 100% efficiency in thermalization, and it's a spherical energy injection. And if you look on this parameter space where the magnetar model can explain things, it looks something like this blue shaded region. There's a limit here to how bright a supernova the magnetar model can make, given the maximal spin we think we have of the neutron star. And this curve here is really reflecting what happens when you change the magnetic field. So there's sort of a sweet spot peak there where the magnetic field is tuned to be just about the right spin down time compared to the diffusion time. And that gives you a peak luminosity of somewhere around 2 to 3 times 10 to the 45 ergs. Which encompasses a lot of the range of the supernova that we see. Here's this debated assassin 15LH, which is really right at the limit of what can be accommodated with the magnetar model. Again, we debate whether it's a superluminous supernova, but it can barely be, it can be accommodated within this model. I just want to mention kind of in passing that mostly I talk about magnetar powering, but there could be another kind of central engine, a black hole at the center. If you could feed it, it may also produce some sort of long-lived energy input. I worked with Jason Dexter, just doing 1D hydrodynamical models of the explosion of a massive star. This is showing you the shock velocity as it goes through the star. And actually, as it passes through these compositional interfaces, there's these reverse shocks which tend to propagate backwards and slow down material. And while this shock will kind of propagate all the way through the star and explode it, this material down here may actually not be high enough energy, high enough velocity to actually escape the ejecta, especially for a lower energy explosion. In fact, if you look at the escape speed, in this case, all this material here is moving slower than the escape speed, so it's bound, and the entire helium core will fall back onto the central object over some time period. And so you can feed the black hole through this kind of continual fallback of the innermost ejecta. You can calculate, at least in 1D, what that fallback rate, accretion rate onto the black hole is, and it depends some on what type of star you have, a red supergiant, blue supergiant, or a helium star. And we can have, but you have accretion rates continuing out to, weeks or months when these supernovae are being observed. And if you assume that some fraction of that fallback accretion is tapped to power some luminosity, maybe say 1% of it, for these typical fallback rates, you can get actually quite large luminosities out of the black hole. So I have the detailed picture of how that works, whether it's through black hole disk winds or jets, is complicated. I won't go into it, but there can be this other sort of engine sitting at the center of supernova. So you can make these models, simple 1D models, where you put in a magnetar energy injection and you try to fit the light curves of some observed supernova. And as you have seen, they can fit the observed light curves in most cases quite well. In fact, the biggest criticism I hear of this model is that it's too easy to fit the light curves of all these supernova, because given the range of parameters you have of magnetic field, spin, ejecta, you have quite a bit of freedom in your the sorts of supernova light curves you can produce. It's not strictly true. I showed you there's some range parameter space that it can and can't fit, but I am sympathetic to that notion that there is some flexibility in this model. So we want to have some more detailed sort of predictions, signatures that may move us to the next kind of what you might call the fine structure, or the second order effects that occur in magnetar supernova. And the main effects are really due to dynamical effects. The fact that when you're dumping in all this energy to the supernova ejecta, more energy from the magnetar than the supernova itself, you really restructure the ejecta in a pretty dramatic way. And that has implications for the light curve and the spectra of the supernova. And so I can mention a couple of those effects, and then I'll show you actual calculations that illustrate them. One is that you'll get this cellular structure, so the magnetar dumping in energy actually blows this bubble, which sweeps the ejecta into this dense shell. And that will have effects on the velocities that you measure, say, in the spectra of the supernova. If the magnetar is strong enough, that shell can actually be driven all the way to the surface of the ejecta, and the shock at the leading edge of it can break out and lead to some burst of emission that may lead to some early luminosity of the supernova and may be connected to some of these double-peaked light curves that we talked about. If the magnetar really sweeps up almost all the ejecta and goes to the outer edge, you might have what I'd call shell blowout. That is, the whole shell gets kind of torn apart and broken up in a way that maybe some of the energy can leak out. And then, as mentioned before, the inner parts of the magnetar nebula are really this hard radiation, X-rays, and so on. And if they're strong enough, they can actually ionize the entire ejecta at some point, and you may actually see that non-thermal X-ray emission escaping directly. And even if you don't see the X-ray emission, the escape of it may lead to some inefficiency in the thermalization, which may have implications for the optical light curves as well. So those are some more detailed pictures that we've seen. The observations are also giving us more detailed fine structure in the light curves and spectra. Here's, Robert already mentioned these double peaked events, which show sort of a first peak that lasts only 5 or so days before the main peak. This first peak is actually quite bright. If you look, it's minus 20. That's quite bright by most standards, but not as bright as the peak itself. And so this has to be telling us some sort of hint at what's going on with the supernova. You may try to explain it doing a circumstellar interaction. Maybe there's 2 shells of material, one small one that you hit and create this burst, and another bigger one that you hit later to create this one. Maybe there's a shell here that creates this interaction burst, and then a magnetar turns on and powers this. I'll try to argue that one maybe somewhat appealing and simple idea is that both these peaks are powered by the magnetar, one due to the emergence of the shock and the rest just due to the continuing heating. Whatever the explanation, it has to be fairly robust. I mean, we see these peaks in most supernova where people have looked early enough to try to see something. It varies in its prominence, but there seems to be some sort of early peak in most of these things. So that's some hint of some mechanism that has to be arranged in most cases. And then Robert also mentioned that you see some interesting undulations in some of these observed light curves, sort of flattening plateaus and so on. I think the Assassin 15LH event also showed some interesting behavior like this. You can also explain this perhaps with multiple shells of circumstellar interaction just hitting multiple things and rebrightening. I'll suggest maybe it's also tied to, and maybe in some cases, thermalization effects in a magnetar supernova. So let me give you sort of the picture of the magnetar-driven dynamics. I'll show some cartoon first and then show some actual calculations. What's going on here, sort of like a pulsar wind nebula, you have the neutron star here spinning down, injecting energy into the center and creating this hot bubble of ejecta that sweeps up, this hot bubble of high pressure region that sweeps up the ejecta into this dense shell. And that bubble is pushing that shell along like a piston through the ejecta and shocking material in the front of it. So the magnetar actually heats the ejecta in two distinct ways. It heats it sort of centrally by direct thermalizing of the energy, and it heats it at the surface, the edge of the shell due to the piston going forward. And the idea is that when this shell may reach the surface here, this energy in the shock may vent and produce something like a breakout event. So here's a 1D model to show you kind of what those dynamics may look like. This is, the supernova ejecta in a simple form. It kind of looks like a broken power law, most of the mass in here in the shallow region and in a steeper outer region, and it sort of transitions at this velocity, which is set by the square root of the energy over mass of the explosion. This is what the ejecta would look like if it was just freely expanding. I'll show you what happens if you turn on the magnetar at the base. And I've scaled out the sort of expansion in this movie, so you just see things frozen in place, but it's actually all expanding. And so here's what happens as you turn on the magnetar. It creates this cavity, this high pressure bubble, and sweeps up all that ejecta into a thin shell. Eventually, in this case, almost all the ejecta is swept up, and you see the shock propagating forward. Eventually, it may reach the surface and vent in some burst of radiation. And you also see the shock sort of running out ahead here as it accelerates down this steep density gradient here. So this is a 1D calculation. In multi-D, you expect this shell to be unstable due to Rayleigh-Taylor instabilities, and that can change things a bit. We've run multi-dimensional calculations to see what that looks like. This is a work with Paul Duffel, who's a postdoc at UC Berkeley, and has a very nice code for doing moving mesh hydrodynamics. And we do basically the same sort of problem where we put energy into an expanding supernova remnant due to the magnetar spin down. And I should mention that similar work was done in the context of the pulsar wind nebula by Blondin down back in 2001, and there was just a very nice paper by Chen Woosley and Sukbold on a similar basic setup of the hydrodynamics here. So you can see what happens in multi-dimensions. We dump in the energy, the expansion scaled out here too as well. And here you see the formation of that cavity here. The shell is now Rayleigh-Taylor unstable and gets broken apart and eventually blows out of the ejecta and starts to shred apart into sort of this filamentary structure. So I'll walk you a little bit through some of that dynamics and what it may mean for the observations. To first order, it kind of looks like the 1D model. You have this sort of empty cavity inside and you have this dense shell, but now that shell's been smeared out due to the Rayleigh-Taylor instability. And there's kind of two important radiuses here to keep in mind. One is this transition radius, which marks where the ejecta sort of steepens and falls off. And once the shock passes that, it's going to start to accelerate away. And then there's also this diffusion radius whereby radiation can actually diffuse out faster than the shock can move. And so once this shock shell reaches the diffusion radius, that's where you expect some radiation to break out. And of course, that diffusion radius is moving in time as the shell is moving out. If you look at the difference between 1D and 2D models, qualitatively you have the same picture. You have sort of this cavity and this dense shell. But in 2D, that shell is smeared out quite a bit compared to the very thin shell that you get in 1D. And this was seen also in the work with Chen and Woosley. This has implications for the velocities that you measure in the spectra of superluminous supernova. If you catch it early, the photosphere will be out here at high velocity. Over time, as the supernova expands and thins, the photosphere velocity will recede until it hits this shell, and then it will basically hang out at this velocity corresponding to the shell velocity. And so you expect to see, and we did see in 1D models here, sort of a plateau in the velocity evolution over time. Here it's in the outer layers of the shell, in the outer layers of the ejecta, and then it kind of hits the shell and flattens here. And you see somewhat of a similar thing in observations. These are observations of 2015 BN showing some sort of flattening of the velocity over time. Whether this can be explained only through a shell-like structure or something else, I don't know, but at least consistent with the presence of a shell-like structure. So when that shell starts to reach this diffusion radius here, the shock material at the surface can break out, and that may vent in one of these breakout bursts. You can kind of see what's going on here in this 1D plot. Here's the shell, dense shell being driven by the magnetar bubble here. You can see the shock at the leading edge that's heating material, and when that shock reaches the surface, there'll be a breakout of material, breakout of radiation. We can estimate when that shock reaches the surface, analytically. Basically, it turns out to be a geometric mean of the magnetar spindown time and the diffusion time, which sets the duration of the light curve. And that happens to be of order days for the typical parameters you see. What's interesting is that when this breakout happens, the ejecta has already been expanding for a period of days or so, so it's much larger than the original star. In fact, it's already out at a few times 10 to the 14 centimeters. And so when the shock breaks out, unlike regular shock breakout in supernova, it's not a quick, hard X-ray burst. It's a longer duration, cooler optical luminosity burst, optical UV. And the numbers work out to be somewhere in the range, just analytically, of what you see in that initial bump. So we tried to model with simple semi-analytic models this shock breakout peak. You get something that looks something like this. Here's the breakout burst, here's the regular light curve, and you get sort of this double peak structure. In this example, the double peakness is not that prominent. There may be a few effects that help distinguish the double peak. One is that it's likely that at early times the magnetar energy is not thermalized effectively, and so that you don't get much heating, which would delay this main light curve. And if you look at, if we make that assumption or based on some analytic models of the delay of the heating for magnetar, you can get a more distinct breakout burst and then a rise for the main magnetar light curve. So I wouldn't take these particular models too seriously as they're, sort of, 1D toy models, but they sort of suggest the right kind of behavior for this initial peak without having to add additional ingredients to the model, additional shells or other sort of things. Now, there may be another thing that makes this peak more prominent, and that may be deviations from spherical symmetry. As we said, the energy deposition is assumed to be spherical, but it's likely to be bipolar. And so we've studied that as well, basically injecting the energy in a bipolar way, basically an opening angle of about 25 degrees here, and see what that effect has on the dynamics of a magnetar-driven supernova. And so that's what this movie is showing you, basically almost some kind of jet-like structure. Again, Rayleigh-Taylor instability set in, and it blows out sort of the poles first, creating some kind of more complicated ejecta structure. So the ejecta looks a lot more interesting in this case. The breakout, the reaching of this diffusion radius happens first along the poles, so you might expect a brighter shock breakout first peak if you tend to be looking along the polar regions. You can look at the ejecta. There's still some sort of cellular structure here. It's broken up, but it's still there. So you might expect this flattening of the velocity profiles as well, but that will be dependent upon your viewing angle too. Here the velocities are moving faster along the polar regions than along the equator. And you also see that there is some cavity carved out of the central region, but it's no longer a spherical cavity. It's more of this hourglass from the input of the jet, and that may have implications for what you see in the late time spectra. Last thing I'll mention is that if you have a strong enough magnetar, this is for spherical energy deposition in this case, you can actually start to sweep up all the ejecta, and as it runs out of that steep region, you almost start to tear apart the shell, at least in 2D simulations, and create this kind of filamentary structure, which actually looks a little bit like what you see in the Crab Nebula. And this may open up gaps in the ejecta structure whereby non-thermal radiation or other energy from the magnetar may escape out. And that may have implications for the evolution of the light curve. Even in a spherical case, as Metzger 2014 showed, the hard energy from the magnetar may be strong enough to actually ionize all the ejecta and produce some escape of radiation, okay? And so the last thing I'll show is if you can model this, again, these are 1D semi-analytic models showing what the effect of that X-ray escape may have on the optical light curve. And so here in this dashed line would be the model you would get if you assume that 100% of the energy from the magnetar is thermalized and comes out in the optical. But if some of that energy escapes as X-rays, as the magnetar ionizes the ejecta or leaks out of this porous region, you get a decreased luminosity here. And you get these kind of bumps in the light curve that are really due to when an ionization front breaks through the surface. So when you ionize, say, hydrogen or something, all of a sudden UV radiation can escape out. You get a brightening in the UV, but a decrease in the optical luminosity. And so some of this bumpy structure and changes in color, say bluening of the spectrum, may be related to this idea of ionizing radiation leaking out. Whether this explains the kind of undulations we see in supernovae, I don't know. So I'll leave it there. This is a summary of some of the structures here. There's actually a lot of different constraints on the model, if you think about it. There's the structure of the ejecta, velocity evolution, and line profile shapes. This chalk breakout peak, if that's what it is, ionization breakout that may modulate the optical light curve. And bipolarity, which may mean that if there's bipolarity, there may be some correlation of different observables, luminosity, velocities, and chalk breakout peaks with viewing angle. So it's still at an early stage in terms of what our predictions will say in detail, but there's some interesting connections to the observations already coming out. Thank you.
So I guess I have two questions. One's probably a yes or no question, and the other one might be a little longer. So Robert Quimby mentioned the relatively shallow P Cygni absorption profiles in a lot of these. Do you think that is consistent or explained well by the relatively thin shell structure that you get from magnetar, more so than, let's say, a pair instability supernova?
That's difficult to say. I don't know if that's yes, no. Okay. A lot of that weakness can be due to the kind of unusual state of the ejecta.
I mean,
for these high luminosities.
Hot and everything, yeah.
So hot that you've sort of ionized a lot of the material, and those line optical depths are just low. Otherwise, it depends when you're observing this thing. If you observe it kind of early times, you're not really seeing the shell yet. You're seeing sort of the regular ejecta that hasn't been receded to the shell yet. And in these later times, you may see some sort of narrowing of the width of the features as they hang out at a certain velocity.
Yeah. Okay, so the other question was more about the host galaxies and how the type 2s are distributed all over many metallicities, and the type 1 superluminous supernovae prefer low metallicities. Most of the type 2s seem to be powered by circumstellar interaction. Maybe 2008 ES is one that isn't. Is there a reason why the magnetar, maybe a stellar structure reason why the magnetar prefers not having a hydrogen envelope in order to make a bright supernova? Like the diffusion time is much longer or something?
There's no obvious reason I would think that's the case. I mean, I think the question is whether there's strong evidence that the magnetar is not operating in some of these type 2 supernova as well. There may be interaction happening as well, but the luminosity that you see, as I said, the total energetics that are coming out of these supernova are still rather high. They can be in excess of 10 to the 52 ergs. So it seems like you need probably some sort of central engine, at least to give you that base energy budget. And then maybe some of that is being tapped through interaction, some of it through continued spin down. So yeah, I think the question is whether we can argue that some of the type 2s are also have magnetar activity if the type 1s do as well. It's just the type 1s are a little clearer because if there was interaction going on, you'd expect to see some signature of it in the spectrum. And there doesn't seem to be any obvious signature of it there.
For your bipolar precursor thing, I'm curious, in essentially every type 1 superluminous supernova where we have data early enough and deep enough, we see a precursor. Would you predict that from your model?
It's a good question. It needs to, these are just hydrodynamical calculations, so I'm not actually predicting the shock breakout signature. I think maybe not for every viewing, well, I think the actual prominence of it would depend upon the viewing angle somewhat, so probably more prominent here than here. But even at a viewing angle sort of equatorially, you expect to see some breakout from this material here. I mean, this is not like a relativistic jet that's beamed along a specific direction. It's a more isotropic outflow. So I would say for a large number of viewing angles, you'd expect to see some breakout emission, and that the actual prominence of it relative to the peak of the light curve may vary from case to case.
I was wondering, Dan, so you're going to have some dynamical burning in the, in a jet-driven like supernova. Do you expect at some point to see the transition between basically the magnetar providing most of the energy output and then the nickel radioactive decay transition into that, particularly at intermediate mass ejecta?
It may happen. So there could very well be nickel produced in the explosion. Now, if it was a regular core collapse supernova, there may be not much nickel as in typical core collapse supernova, but some of that may get mixed out in this dynamics. Whether it would ever dominate over the magnetar, I'm not sure. Probably not. I mean, the nickel decay cobalt decay is happening sort of exponentially while this magnetar just has a power law fall off. And also the thermalization of the magnetar energy is probably more efficient out to late times because the energy is not just coming out in gamma rays, which are eventually escape pretty easily. It's coming out across the electromagnetic spectrum in X-rays that are more easily absorbed. So one would have to do a detailed calculation with both components in there, but it could contribute, but may not dominate at any point in the light curve evolution.
But remember that the jet-driven supernova are thought in similar configurations to provide 0.1 solar masses of nickel, no?
Yeah.
Over those solid angles. And if that was a spherical, you probably get, close to 0.5 solar masses of nickel.
Yeah, I mean, I should say here, this jet-driven thing, of course, this is already after the supernovas exploded, right? So the star material is already expanded to some low-density state, and then you turn the magnetar on over a period of days or something, and it creates there. So although you get, kind of high temperature, well, you don't even get that high at temperatures here because the things are expanded and the densities are low. So you probably don't get any burning in the magnetar-driven shock, but you may have made some in the initial explosion.
So you mentioned on your conclusions slide that once you have this ionization breakout, you would also see some modulation of the optical radiation. Could you comment on what kind of modulation?
Well, that's what I was kind of getting at here. So the idea is that the energy from the magnetar in that wind nebula is basically coming out across the electromagnetic spectrum. And for certain parameters or for certain early times, all of that magnetar energy can get absorbed and thermalized and re-rated in the optical. But at later times, some of the X-ray or UV radiation may break out, ionized material escape through these channels, and then the optical luminosity will drop because basically some of the energy is getting out at other wavelength bands, and that may lead to these sort of sharp drops or plateaus in the luminosity, because when ionization breakout happens, when you suddenly ionize everything, all of a sudden the X-rays can escape. And so you have a sudden increase in the X-ray luminosity and a sudden concomitant decrease in the optical